welcome to the video on antiderivatives, also called the indefinite integral. So first we're going to start with antiderivatives, okay? So what is an antiderivative? So anti means opposite of or against. So antiderivative means basically the opposite of a derivative, okay? So a function, we say that a function, and I'll call it capital F of x, is an antiderivative, so I'll just abbreviate antiderivative, okay, of a lowercase f of x function on an interval ab if we have that f, the first derivative of capital F function is equal to our original, or our lowercase f function for all x within AB, or on that interval. Okay, so what that means is that, for example, let's say we have some kind of, so here's our example, f of x, capital F of x, is equal to a cosine x. So therefore, our so this is an antiderivative. This is an antiderivative for, or of, we're going to say of f of x is equal to negative sine x, right? Because then we have that if we derive our capital F prime of x, we get negative sine x, which is then equal to our lowercase f of x, okay? So that's what an antiderivative is, and they aren't unique, meaning there isn't only one solution. The capital f of x can always differ by a constant because that disappears in the differentiation. So let me show you an example of that. So the concept here is that capital F of x can always differ by a constant, meaning a number, constant, because it disappears anyways when you differentiate in the differentiation. Okay, I'll just abbreviate differentiation. Okay, so let's see an example of this. Let's say we have an capital F of x that is equal to, let's say, our cosine x plus 3. Okay, and let's say we also have one where our f sub 2, this is just our second equation, is cosine x plus 7. Okay, so let's differentiate both, and we get f prime of x is equal to negative sine x, and then that constant turns into a 0, so it doesn't matter, right? If we differentiate this one, then we get a negative sine x, and then again plus a 0, because that constant goes away. So basically this constant here in our antiderivative, it's not going to matter, right? Or it can differ, and we still get that same derivative of the capital F function. So therefore, these here, they are both with the 3 and 7, okay? So these are both antiderivatives. Both are valid antiderivatives for the function derivatives for lowercase f of x is equal to a negative sine x, okay? So both of them can serve as an antiderivative. Alright, so as far as antiderivatives go, integration, which we've learned a little bit about. So integration, denoted by this sign here, right, is basically the process of finding an antiderivative, an antiderivative, okay? Derivative. And by that, I mean, if we have this integral sign here, and we have our original function, lowercase f of x, and then our dx, what we're going to get out is the capital F of x, and then we also have to have this plus c, which stands for that constant, which may vary, okay? And that is usually unknown, all right? So then we have, then our d dx, the derivative of the right side, our antiderivative, plus c, that's going to equal the derivative with respect to x of the left side, right? So we have this integral sign, f of x dx, all right? So then we see here that this part becomes derivative of this and derivative of that, but the derivative, okay, so first of all, we have capital F prime of x plus, and then we get a 0, right, because that constant goes to 0. And then on the right side, we have that the differentiation, and integration, those cancel out because they're like inverse functions or opposite functions. So we just get out this f of x, okay? So then we see finally that f prime, capital F prime of x is equal to lowercase f of x, which again shows that we have the antiderivative, all right? And here, if you'll notice, in this integration sign that I drew, there are no limits of integration, a to b, so this is what we call an indefinite integral, okay? Indefinite, that's the important part. So that means we have no limits of integration. When we do stick in those limits, like a and b, then we call it a definite integral. But here, when you don't have limits, then that would be an indefinite integral. Alright, so some of these cases of integration can be evaluated by reversing our differentiation rules. So, for example, here's the power rule, alright, but it's going to be rewritten for integrals. So, let's say we're starting with some x to the n, and then we want to integrate it. Okay, integrate with respect to dx, with respect to x. So this is actually going to give us something like 1 over n plus 1 times x to the n plus 1, and then plus c. And then this is for n is not equal to negative 1, because we don't want a 0 on the bottom, right? So anyways, you can always check this by differentiating. So let's do so. So we have d dx of the integral of x to the n dx, and then on the right side we also have d dx of all of this 1 over n plus 1 times x to the n plus 1 plus c. So on the left side these things cancel out, right? So we just got out our x to the n. And then on the right side, according to the power rule, we're going to bring that guy down in front. So we have an n plus 1 over an n plus 1 that was already there times x to the n plus 1, and now we're going to subtract 1 from the power, and then this thing just goes to 0, so plus 0, okay? So we have x to the n is equal to, these cancel out to make a 1, and then, so we have 1 times x to the n power, because those 1's cancel out as well. So we have x to the n, and we're good, right? So that power rule works. So here's our power rule for integrals, right up here on that top line, okay? Alright, so now let's explore another rule for integrals. So now we have the ln x1. So this is a special one. So this is when our n does equal negative 1. So let's say we have something like, we're trying to take the integral of dx over x, also known as, we could just separate those. So 1 over x times the dx. So what do you do with this? Because if you use the power rule, then we're going to get a 0 on the bottom, which is kind of weird. So anyways, what we're going to do instead is, this is actually just the rule for the integral of this is ln of absolute value x. And then we have that plus any constant, right? So for x is not equal to 0, okay? So, and this is true because, and let's check by differentiation, right? So because our d dx of the integral of 1 over x dx would then be equal to d dx of the right side, so this thing over here. Okay, so if we differentiate that, we have ln of x plus c. So if we differentiate the left side, we just get this 1 over x out. And then over here, we get a 1 over x out as well. Okay, so this that constant goes to 0, right? So that's not even there. Okay, so this does work. So this is our ln x rule. Alright, and then don't forget that for x is not equal to 0, right? Okay, so let's do a practice problem. What we're going to do is use the power rule for integrals, this is, to integrate the following problem. Integrate, and then I'll give you the integral. So integral of 4x to the third minus 2x squared plus 5, and then we have our dx. Okay, so the first thing that we see is we can actually break up this long thing by the subtraction sign and the addition sign. So what I mean by that is this is going to equal the integral of 4x to the third dx. Okay, so that's by itself. And then we break it up with the subtraction sign. So it's kind of like we're making little islands of the terms, right? So 2x squared dx is the next one, and then there's that addition sign, and then we have, so plus the integral of 5 dx, okay? So now that we have that, we can actually take out these constants in front, right? That's like the constant multiple rule. Okay, so we're going to take out all 3 constants here. So then we get 4 times the integral of x to the third dx, okay? And then we have minus a 2 times the integral of x squared dx, and then plus a 5 times the integral of 1 dx, okay? So that one's just a constant there. All right, so now what we're going to do is just use the power rule, right? So what we're going to have is a 4 times, and then now that we have this x to the third here, what we're going to do is add 1 to the power, so x to the fourth now, and then divide by that new power, so 1 over 4, okay? And then for the next one, we have that 2 just sitting in front, and then when we deal with this guy, the x squared, we're going to add 1 to the exponent, so that'd be a 3 now, and we're going to divide by that new exponent. Okay, and then the next one, this 1 is actually like an x to the 0 power, right? So if we add 1 to that power, we just get x to the 1, and then if we divide by that, we get 1 over 1. Okay, so here we see that the 4's on this term cancel out. Then here we get a 2 over 3, and here we get a 5. Okay, so I'll write the answer on the next slide. All right, so once we integrated, we got a 1 times x to the fourth, and then minus a 2 over 3 x to the third, and then plus a 5x, and also we can't forget our plus c, remember? So when we integrated, I was actually supposed to write that on the previous step, but when we integrated, whenever you integrate indefinitely, meaning without limits of integration, you always have to have this plus c here, because remember, antiderivatives are not unique, they can differ by a constant, okay? So this is basically our answer. I'll write it where we don't have the obnoxious box in the star. So this is going to be x to the fourth minus 2 over 3 x to the third plus a 5x and then plus a c, and we just leave it as such.